And now? Yeah, okay. Okay, so good morning, everyone. Thank you very much to Lorenzo and to Neil for inviting me to take part in this very nice morning at the end of the school. So I thought I would talk about something that I'm working on at the moment, which is high-dimensional mediation analysis. But I recognize that many people are not interested in high-dimensional anything or mediation anything. So I hope that it does have some relevance, even if you're not interested in either of those things, because I'm going to try to say a little bit, not about what I have done at all, but what I've learned from what other people have done about the use of machine learning statistical methods in epidemiology, which I think is something that's quite topical at the moment, and in a way goes some of the way to address one of Carolina's very important points this morning. So I should also acknowledge my funders, the Wellcome Trust and the Royal Society, and also my collaborators who have helped me with every aspect of this. So I should also apologize that I think a good statistical talk should have a good motivating problem, a good statistical solution, and then the important final part where you apply the solution to the motivating problem and solve everything there, and I don't have the third part. I'm still working on that. So I'm afraid I will describe to you the problem and a possible solution, but it will not really have the nice conclusion that it should have. So as everybody knows, the recent advances in DNA sequencing technologies have led to this sort of genomics revolution where we now have tens of thousands, if not more, of known sort of robust gene-disease association discoveries. And some people argue, and I'll say a little bit more about this in a moment, that knowing that a gene causes a disease is not as valuable as knowing how the gene causes that disease. In other words, for example, by perhaps affecting some blood biomarkers that go on to cause, let's say, cardiovascular disease based on some known SNP. And likewise, biomarker measuring technologies have come along a huge development recently. So there is this omics revolution, more than just the genomics revolution. And so the problem I'm working on is how one goes about doing some kind of mediation analysis. By that I mean partitioning, if you like, of the effect of a gene on an outcome via many different mediators, or in this case, these blood biomarkers. And so I just want to say a little bit about why I think mediation analysis is valuable in this context. I have a little bit of a bugbear that often people do mediation analysis when it's not particularly maybe the question of scientific interest, but I think there is value to it here. So, of course, biologists know quite a lot about the gene-disease pathway, if you like. It is known, and I'm sure people in this room know far better than I do, but my very basic understanding is that genes are transcripted, they create proteins that go on to create metabolites that then have a part in causing diseases. And of course, there are many other aspects also in the picture, like the environment and all these kinds of interactions that I'm not depicting here. But the fact that this chain is in some sense understood, or at least partially understood, helps in a certain sense. And one thing that is of interest is this concept of the druggable genome, the concept that at least some drugs work by mimicking or in effect cancelling out the effect of genes. So again, I'm not claiming to understand this very well, but what I understand from my colleagues is that you can think of some drugs as interfering in this chain in some way. And so I think the use of mediation analysis here is therefore linked to this idea that suppose we did know what are the important biomarkers that mediate a particular druggable gene to disease relationship, then that would act as a sort of proxy for understanding what would lie on a causal pathway between the drug, if it existed, and the disease. And this could therefore be used to decide maybe on the most promising potential drugs to be developed, or perhaps to suggest promising combinations of drugs or second-line drugs when a particular drug is not tolerated. Maybe it could be useful in the area of personalized medicine, where you want to think what drug would suit somebody with a particular biomarker profile. And obviously in future clinical trials of new drugs, then maybe knowing about the biomarker mediators, you could choose sensible surrogate endpoints. So in my view, mediation analysis does see, if it could be done, does seem potentially of value here. So okay, if we accept that that's a sensible job to embark upon, there are obviously going to be many challenges. So first of all, the biomarkers, my set of mediators, are going to be high dimensional. So typically you will have around 200 metabolites measured in a particular sample. 4,000 proteins are not uncommon. And we want potentially to separate the effect of the gene on the disease via each of these things separately. These biomarkers are almost certainly going to be highly correlated due to unmeasured common causes of these biomarkers that we won't know what many of them are. So that's what I'm showing by this sort of unmeasured set of things, we don't even know what they are here, that are common causes of this block of biomarkers. We typically won't know the causal ordering between the mediators, the biomarkers, if there is one at all. And biomarkers tend to have quite strange distributions. This is not an atypical sort of distribution that you might find for a biomarker. And then the statistical dependence of the disease on the many biomarkers is also going to be typically very difficult to model correctly. And the more biomarkers there are in the picture, the more difficult, the more mistakes, or the more our mistakes in the modeling can propagate into larger mistakes in the final conclusion. So the strategy that I'm going to adopt is in order to deal with the high-dimensional mediators that are highly correlated due to largely unmeasured common causes and for which we don't know the causal ordering, I'm going to focus on a particular sort of mediation effect called the interventional multiple mediator effect. So those of you who were fortunate or unfortunate enough to follow the mediation analysis course this week, you probably thought you'd seen interventional multiple mediator effects for the last time in your life, but I'm afraid there is one more that you have to put up with this morning. But those who are not in the course and who may not know what they are, in a sense, don't worry about that now. Just trust me that it is a sensible way of quantifying the indirect effect through a particular biomarker. And so we are going to have many, many of these indirect effects. And then to deal with the fact that the biomarkers have strange distributions and that the statistical dependence of the outcome on these many biomarkers is going to be essentially impossible to model correctly using conventional techniques, I'm going to focus on data adaptive estimation. By that I mean machine learning algorithms, these modern computerized techniques for predicting one variable from a bunch of other variables. So here are some few more details. So here is the way I write down my indirect effect. So this is the effect that I'm proposing we are interested in estimating. Again, don't worry about the details of the maths here, but what I want you to notice is that it has many components. It has a conditional expectation here. It has a difference in conditional densities here. It has another density here. And this difference in densities here means that what we're capturing is the effect on the risk of the outcome of shifting the conditional distribution of a particular chosen biomarker that I'm now just calling MJ, an arbitrarily chosen biomarker out of our huge set, given confounders from what it would be in the absence of the gene to what it would be in the presence of the gene. This is this change in distribution here. And supposing that the distribution of all other biomarkers remains as if the gene were absent. So this is just a way of quantifying the indirect effect through a particular biomarker. So this can be identified under a certain set of assumptions. And the assumptions we're going to make are that there is no unmeasured confounding of the gene and the whole set of biomarkers taken as a set, no unmeasured confounding of that set of biomarkers and the outcome, nor of the exposure and the outcome. That sounds like an awful lot of assumptions, and they are. They are strong assumptions, and there are many of them. But I want to point out that there are many assumptions we are not making as well, which is a bonus. So we are not making any assumption about there being no unmeasured common causes of one biomarker and another. So if you like, there is unmeasured confounding between the M's that we're not assuming is not there. And we're also agnostic as to any causal ordering between the biomarkers. So that's a nice thing. The effects, together with the interventional direct effect, do not sum to the total effect. That's a drawback. But one appealing nature of the definition is that it is symmetric in the choice of biomarker. So essentially, we have one definition of an indirect effect that is the same for each of the biomarkers. We just change which biomarker sits in this position of being MJ. So, I mean, we could debate for hours about these assumptions and whether this is the sensible estimand to focus on. I think it's a nice one in terms of the trade-off between what we're actually interested in and what we can plausibly justify the assumptions for. But because I want to focus in the talk on the estimation aspect, I'm going to take this now as if we are happy that this is the estimand of interest and that it can be identified under these assumptions. So under those assumptions, we can rewrite the estimand as a function of the distribution of the observed data. So that's our first step. And I just want you to notice that, again, this is a conditional expectation, this is a conditional density, this is a conditional density. So there are many components to this estimand that if we are going to form an estimator, we need to estimate. So the kind of obvious estimation strategy is to hat everything. And what I mean by that is these are all unknown statistical quantities, but we have data on the variables that these unknown quantities describe the distribution of, and therefore we can estimate these quantities individually from the data and plug those in. And that's what's called plug-in estimation. And it's sort of the most obvious thing to do. So for example, this is a conditional expectation. So what people might do, suppose that y is binary, is to fit a logistic regression model for y, given the confounders, the exposure, and the biomarkers, and then just predict this conditional expectation, which would be a conditional probability of y equals 1 if y is binary, and plug that in. And we know that typically what people do is they fit a logistic regression model with just main effects. Or maybe, if some of these confounders or many of these mediators will be continuous, they might look at whether you need is M1 enough, or should we put an M1 squared in? Or maybe we need an M1 squared times X. And, people will fiddle around with their models. And this is one of the things that Carolina was talking about that would essentially lead to everyone in this room ending up with a different answer. And not only would everyone end up with a different answer there, they would end up with a different answer here and here and here. And it's sort of part of what makes a slight mockery out of the statistical analysis of epidemiological data. So in other words, the obvious parametric estimation strategies would be heavily reliant on and sensitive to misspecifications of a huge number of parametric assumptions that we essentially could not justify. And even if you think that you're very good at looking at data, people, often statisticians and epidemiologists, think they do have a sort of sixth sense of when to add an interaction term, when to add a square term. But you can imagine if you've got 4,000 M's, then even, in the time that you have, even if you're very good at it, you'll be very stretched to come up with a plausible model for these things. So essentially, people are probably just going to fit a very simple model without really checking it at all. So to overcome that threat of model misspecification, we could plug in machine learning fits for the hats. So we could say, OK, I'm not as good as my computer at predicting y from C, X, and M, so I'll give that task to the computer. I'm not saying we give all the tasks to the computer, but that is a task that a computer is very good at doing. And that's known as machine learning. And in particular, there is a very appealing, relatively new technique called super learning, or it's an example of ensemble learning, where what you do is you have not just one machine learning algorithm, because now there are many, many machine learning algorithms. So even that would be subjective, because I might choose one, you might choose a different one, and we end up with different results again. But the idea of ensemble learning is that you put every machine learning algorithm you can think of into the library of this ensemble learner. And it splits your data into 10 parts, let's say, and it chooses the best prediction for your quantity of interest. Let's focus on this conditional expectation, using a technique called cross-validation. So it splits your data into 10 parts. For each candidate algorithm, it tries it using 9/10 of your data and tests it by predicting the 10th of the data that it hasn't used to fit the model. So it can assess how good those predictions are on the 10th of the data that you haven't used. And then you cycle through, each 10th of the data gets its turn to be the 10th that you're testing the algorithm on. And that means that you can rank all of the algorithms in terms of their predictive ability. And this avoids overfitting, because if you're overfitting on your 9/10, you won't predict your final 10th well. So it finds a bias variance trade-off in this prediction game without any risk of subjectivity, and it really can be shown to do a much better job than a human being can do. And rather than even just picking the best algorithm, it will give you the best convex combination of all possible algorithms. So you really end up with something which can be, I think, quite reasonably called optimal if the things that are in the library are sufficiently good. And the point is you don't need to know what's in the library. You can keep adding more and more things into the library. You can even put really bad things in the library. You don't need any quality control. Because if it's a very bad model for predicting, a very bad algorithm for predicting what you're trying to predict, then that bad algorithm just won't be selected. So it won't really affect things in any negative way. So that sounds all very good. However, unfortunately, if you do that, you plug in your machine learning fits here, your machine learning fits here, here, and here. The resulting estimator that you get, in other words, this estimator, this plug-in estimator, now with the machine learning fits, typically needs an unreasonably large sample size to settle at a value. This is, in statistical jargon, you say that it has very slow convergence. That just means you really typically need a huge sample size for the thing to be practical. In addition, because many of the algorithms that you'll be using are highly non-regular, so they're strange algorithms, if you like. They jump about, they're not smooth, they're not regular in most senses of the word. They actually imply, the use of these algorithms imply a very strange distribution for the resulting estimator, which makes valid inference, which I mean, getting good standard errors, valid confidence intervals, p-values, etc., essentially impossible. And even the bootstrap, which is what we tend to use when nothing else works, is also invalid when you have this non-regularity in the estimation. So just to show us a picture, here is an example of what the distribution of this estimator might look like when you've used these machine learning fits in here. So you see it's very bumpy. It has this huge spike here. It's very far from being normally distributed. And so standard inference just can't really be done. And not just standard inference can't be done. There aren't, at the moment, any alternative inference methods that would give you valid inference in this situation. So even though it's a nice idea, it's good for prediction, but it's not good for statistical inference. So to summarize, if we're comparing plug-in estimation using parametric models, this is when everybody chooses their favorite logistic regression model or whatever, versus machine learning, then typically the parametric version will be the more biased one, because unless miraculously all the models are correct, we know we will get bias. Machine learning will typically be less biased. Parametric models are typically more precise, but if they're biased, you could say there's no point in being precise if you're biased, whereas the machine learning technique arguably gets this bias variance trade-off optimized using the cross-validation method. Parametric models, we've already said, are subjective. The machine learning is at least more objective. It's getting as close to objectivity in data analysis that I think we can get at the moment. But inferences are, okay, difficult even in the parametric sense, but at least the bootstrap works. Whereas with machine learning, inferences are essentially impossible, and even the bootstrap doesn't work. And the convergence here is fast, but to the wrong place, and the convergence here is slow. So essentially, we have nice green good things up here and bad red things down here. So the holy grail would be an estimation strategy that uses machine learning to take advantage of all these things, but somehow has good convergence and tractable inferences, so solves these problems. Now, there is a statistician in California called Mark van der Laan, who has been writing now for about 10 years about his suggestion, targeted minimum loss-based estimation, called TMLE, using the superlearner. And he claims, and mathematically shows, not just claims arbitrarily, that he can do exactly this. So he says that using this method, you get all of the advantages of machine learning without any of the disadvantages. And so this is what I thought must be very useful for my problem, so I spent a lot of time trying to understand this. And the key to TMLE's success is that the constructed estimators are not the one I just showed you. It's not that simple plug-in estimator. It is a specially constructed estimator that has a particular orthogonality criterion known as Neyman orthogonality. So essentially, the estimator ends up being orthogonal to all those little bits that you have to estimate, those nuisance parameters in the expression. So I thought, proceed with this for my problem. So using very useful theory from semi-parametric statistics, we've derived a Neyman orthogonal estimator for our indirect effect through biomarker J, if you remember. So it's even messier than the previous thing. And again, I'm not asking you to follow what this is, but the point I'm trying to make is that it again is something with a huge number of hat quantities. And these are all things that we have to estimate using the data, and we can do them, again, either parametrically or using machine learning fits. But if we use machine learning fits, because this estimator has this Neyman orthogonal property, which if I try to explain it intuitively, it's all to do with the fact that there are always more than one hatted thing multiplied together. And so you end up with that irregularity that we had before, but you always have more than one irregular thing multiplied together. And because the irregularities are also small, if you imagine multiplying a small, bumpy, nasty thing with another small, bumpy, nasty thing, you end up with a much less bumpy thing because it's the smallness of the two things that dominates rather than the bumpiness. So it's almost like what we had before was first-order bumpiness. Now we have second-order bumpiness. So, and it also actually has other advantages in terms of convergence rates and robustness as well. So here's an example. We had this bumpiness in the first-order thing, and now I've superimposed what the distribution of the corresponding Neyman orthogonal estimator would look like. And you see it looks much more like a normally distributed, nice, neat curve. So it means that we can use machine learning for the fits and get standard inference really easily and valid confidence intervals and beautiful statistical inference as we want. So I'm sure I'm running out of time, but I just very quickly want to convince you of one other thing. So I want to convince you that it is worth doing this machine learning, because I think often we think, well, surely we know that our parametric models are wrong, but maybe they're close enough to being right that it doesn't really matter. There's sort of all models are wrong, but some are useful argument. So I just have a very quick, simple simulation study to show you how wrong you can go with parametric fits. So I won't go through the details, but I'll just show you the DAG. So it's actually a very simple problem with only 3 mediates, 3 biomarkers in my simulation. And I've simulated such that the gene affects M1 and M1 affects the outcome. But M2 doesn't affect the outcome, and the gene doesn't affect M3. So in fact, M1 is the only actual mediator, you see. So I set it up like this so that I had a very clear way of judging whether the estimator is working well or not, because I should be picking out M1, if you like, as the mediator that is truly mediating my XY relationship. I simulated some confounders, and in the easy situation, it was just like this. In the easy situation, these were multivariate normal. The true distribution of Y given M, X, and C was a very simple main effects only linear regression. So it was very easy for the parametric fits to do a good job, if you like. But then in the difficult situation, I added unmeasured confounding of these things to make them quite highly correlated, which in itself is going to make things more tricky, because if you get slightly wrong models, you may pick up the wrong mediator as being the actual mediator. I also then simulated my mediators not to have a multivariate normal distribution, but to have a very strange distribution, and I also made the dependence of Y on M to be slightly unusual, not a standard model. So then I've just compared the name, both estimators are the name and orthogonal estimators, the complicated one that I showed. But in the first instance, I just put my parametric fits in for all of the hats. And in the second one, I put the superlearner fits. And so in the easy situation, where the parametric models are in any case correctly specified, we see that the parametric hats, if you like, when we put our parametric hats on, we do a perfectly reasonable job. And as the sample size increases, we get to the stage where we're always picking out M1 as being the true mediator. That's what we would expect. It is worth looking at the superlearner hats, because you would think that maybe when the parametric hats actually are right, then you're going to lose something by being so flexible with your superlearner hats. But in fact, the performance is not really noticeably any worse. Even though we don't need the superlearner here, we still don't lose anything by using it. Whereas now in the difficult scenario, the parametric hats become disastrous. There's a large bias. We only 40% of the time pick out that M1 is the true mediator, whereas the superlearner fits do a much better job. So this is just showing that under relatively mild misspecification of the parametric models, if you have very correlated biomarkers, you will end up with the wrong conclusion using your simple parametric models. And when I showed this to some more practical statisticians, they said, but I never would have assumed multivariate normal for my mediators, having graphed them and seen them to be all skewed. I would have log transformed them, and I'm sure all the problems would have gone away. So just to show the parametric fits after log transforming the mediators actually do no better in this example. So this is obviously work in progress. There is still a lot to do. I want to do far more extensive simulation studies, and this is, arguably quite selective, which we've learned this morning we shouldn't be at all. So there's a lot more thorough investigation of these things to be done, but I think so far the proposal looks promising. I haven't showed you simulations with more mediators, but the ones I have done show that the method does actually seem to scale up well to having hundreds of mediators, even though I've only shown you an example with 3. So the next step is applying these methods on real data. So I'm using the UCLEB consortium and UK Biobank data, and of course there are myriad new complications that come with real messy data. So there's time to event outcomes, multiple studies, repeated metabolomic measurements, and all kinds of things that we need to extend to, but that's all on the to-do list. But then a general comment about machine learning in epidemiology. So I think as data sets continue to get larger and more complex, and as the criticisms of our field, the famous most published research findings are false, intensify. And I do agree with the comments that have been made this morning that, in a sense, many research findings should be false. That's how science is, and that's how progress is made. But I do think that there are certain aspects where we are more wrong than we need to be, and I think the use of parametric subjective statistical models is an example of that, where there is an easy fix, we have it available, so we should be using it. So I believe that we will be forced, and we should be forced, to adopt more scientifically sound objective data analysis techniques that are less prone to the kinds of biases that Carolina was talking about. So the superlearner, I think, is perfect for this. However, as we've seen, to get estimators then with good small sample properties and tractable inferences, we can't simply use machine learning methods in the most obvious way, i.e. plugging them in where we would otherwise have plugged in our parametric models. So really, we have to use them in conjunction. And this is not just for the high-dimensional mediation setting. This is for any setting. In order to get valid inferences following machine learning nuisance model fits, we need to use them in conjunction with these name and orthogonal estimators, which are not ever straightforward to derive, I think. So this is good news for statisticians because it means there's still work for us to do in deriving the name and orthogonal estimators, even when the machines have taken over everything else. And that's it. Thank you for listening.